Hello everyone, my name is Abhishek and I'll be presenting WedgeBlock. WedgeBlock is a work that is done in collaboration with researchers from UC Irvine, UC Davis, and New Jersey Institute of Technology. The motivation for WedgeBlock stems from decentralized applications. Decentralized applications have clients. They have an application that is deployed very often in cloud nodes. The main factor behind decentralized application is the support of the public blockchain, where applications store their smart contracts, business operations, data, and other important information relevant to the clients on the blockchain, and thus making it transparent. Applications also have off-chain storage, where they store application logs and application data. However, these logs are quite large and cannot be stored on the blockchain. The blockchain provides security for the data that is stored on the blockchain in smart contracts in terms of tamper resistance, open data storage. However, these properties are not shared in the off-chain storage. Existing approaches that help augment this lack of security in off-chain storage fall into three categories. The first category is the baseline category, where you store everything on-chain. There is nothing that is stored on the off-chain data. This is both expensive as well as slow. The second approach is to store off-chain data in the off-chain node. However, this data is encrypted, and digests are stored on the blockchain that allow this data to be verified at a later stage. The third is to use trusted execution environments that ensure that the data that is stored on the off-chain node, as well as the process of storing and executing these requests, remains trusted. A common theme in all of these approaches is to make the off-chain storage more secure. WedgeBlock also goes into the similar direction. However, we take a different approach. We ensure that the off-chain storage supports same, if not exactly the same, properties that data on the blockchain supports. We ensure that the data that is stored on the off-chain node is correct. However, we ensure that this data is the process of ensuring data integrity is lazy. It does not require synchronous communication between clients and off-chain nodes. We also ensure that this data is minimum amount of data is stored on the blockchain. We don't want a lot of data to be stored. That increases the cost of operating the blockchain. Lastly, we ensure that although we ensure that the data on the off-chain node is correct, we also create an avenue for clients to punish misbehaving or malicious off-chain nodes. And this entire process we call lazy minimum trust, and this is the core of WedgeBlock. In order to support this aim, we augment the design of off-chain applications by adding additional storage and additional smart contracts that allow WedgeBlock to support the goals. To provide an interface for clients, WedgeBlock allows data to be appended or to be read from the off-chain storage. The security model that we follow is that we ensure that all nodes that are participating in the WedgeBlock infrastructure are considered untrusted and potentially malicious. All data is cryptographically signed, and all messages are identified to the sender. All data, the communication model is partially asynchronous, and the punishment model enforces all or nothing. That is, you either get punished completely, you lose all your escrow funds or data or monetary investments, or you don't lose anything. There are two stages for request processing in WedgeBlock. The first is the off-chain commit, And the second stage is the blockchain commit. In the first stage, the client sends some data to be written to the off-chain node. The off-chain node creates a log entry, stores batches of those data into the log, generates a Merkle root, and this Merkle root creation is then committed to the off-chain storage. This completes the off-chain commitment, and a response is sent back to the user saying with the proof, with the Merkle proof. In stage 2, the root that was generated, the digest, is returned to the blockchain. This ensures that the client can then validate data from the blockchain to ensure that the off-chain node had written the correct root onto the blockchain. The smart contracts that are used in WedgeBlock are of 3 types. One is the root record contract that stores the digests, provides the interface to store and retrieve digests based on the indexes. The second is punishment contract that enforces punishment on the off-chain node in case the client generates a proof, shows a proof that the off-chain node behaved maliciously. And the payment contract allows the off-chain node to be paid. 3 specific purposes: store digests, pay the off-chain node, or punish the off-chain node. To experimentally evaluate WedgeBlock, we use 2 metrics. One is latency of executing the requests on WedgeBlock, and the second is monetary cost, which is the cost of writing data onto the blockchain in the cryptocurrency. And we then compare WedgeBlock's performance with similar systems. The experimental setup is shown here. We have 3 client machines that push requests onto the off-chain node, and we use the Ropsten testnet to test our smart contracts on a realistic Ethereum setup. The existing work that we compare WedgeBlock with fall into 3 categories. The first is on-chain logging, the second is synchronous off-chain logging, and roll-up inspired hybrid logging. On-chain logging stores data directly onto the blockchain. There is no middleman to store the data. In second case, off-chain node performs synchronous writes to the blockchain and then responds back to the client. In this case, only after the response has been generated by the blockchain will a response to the client be sent. In hybrid logging, this is roll-up inspired, where you have much of the work that is done on the off-chain node. However, log digests are also written to the blockchain. As we can expect, OCL performs the worst because we need to both write to the blockchain everything that the client wants to write. Thus, it has bad throughput and bad monetary cost, higher monetary cost. SOCL performs better. However, the throughput is lower. The monetary cost per operation is also lower because we can batch multiple digests and write them to the blockchain. RHL performs well in throughput. However, since we write everything onto the blockchain, the monetary cost is high. WedgeBlock is the only system that performs well in both scenarios. In conclusion, we would like to say that WedgeBlock introduces the idea of lazy minimum trust, which ensures that DApps can perform in a trustworthy manner. We build on the smart contracts infrastructure that the blockchain allows to build a holistic system that allows clients to both access off-chain nodes as well as to pay them and punish them, thus reducing the latency of request processing at the off-chain node and allowing the off-chain nodes to also be paid as well as punished. With this, I conclude. Thank you.